Imagine sitting at any point in space, many tens of billions of years from now, and watching the universe stop expanding. There would be no sound, there would be no boundary, there would be no force visibly arriving. The galaxy clusters around you, which had been receding for the last 80 billion years, would simply slow. Their redshifts would drift downward. The far galaxies would slow first, then the nearer ones. And then, quietly, over a span of time longer than anything human civilization has measured, the redshifts on the most distant galaxies would invert, and the universe would, gently, begin to come back. This is not a horror movie. This is not a sudden event. This is what the math of a recollapsing universe actually predicts. And the data from a single survey released this year has put that scenario, for the first time in 27 years, back on the table. Get cozy. Hit subscribe if this is your first time, because by the end of this, the universe ending will not feel like an ending at all. Now let's gently fall into this. Part 1. The telescope that is listening tonight. There is an instrument in the Arizona desert that may decide how the universe ends. It sits at the top of a 4-meter telescope on Kitt Peak, about an hour west of Tucson, at an altitude of just over 2,000 meters. The telescope itself is older than most of the people working with it. It was completed in 1973. It has been pointed at the sky for half a century. And inside its prime focus, mounted at the exact spot where light from distant galaxies converges before it would otherwise scatter, there is a circular array of 5,000 robotic fibers. Each fiber is about the width of a human hair. Each one is mounted on its own small motorized positioner, and every clear night those 5,000 fibers reseat themselves between observations, aligning to the precise sky coordinates of 5,000 individual galaxies, then drinking in their light for a few minutes at a time before moving again. The instrument has a name. It is called DESI. The letters stand for Dark Energy Spectroscopic Instrument. It began routine survey operations in May of 2021. By April of 2024, it had measured the redshifts of approximately 6 million galaxies and quasars. By March of 2025, that number had grown to roughly 14 million. It is now the largest three-dimensional map of the universe ever made by any instrument in any era of cosmology. And what it has been measuring is not, on its face, exotic. It is the slow, methodical, almost industrial accumulation of galaxy redshifts. Slot a fiber on a galaxy, record the spectrum, move the fiber, repeat, 5,000 times, every few minutes, every clear night, for years. But buried inside those redshifts is the answer to a question that physics has been asking, in one form or another, since 1922. The question is not whether the universe is expanding. We have known that since Hubble's 1929 paper. The question is what the expansion is doing now and what it is going to do next. And the answer DESI has begun to suggest, in 2 separate data releases over the last 20 months, is one that physics had quietly retired in 1998 and had not seriously revisited since. The textbook ending of the universe, as it has been taught in every cosmology course since the late 90s, is heat death. The universe expands forever. Galaxies recede past one another. Stars use up their fuel. Black holes evaporate. Eventually, after timescales so long, the word eventually loses meaning. The universe enters a uniform, cold, low-density state from which nothing further can happen. That is the ending the data supported. That is the ending the math required, given a cosmological constant. That is the ending the listener has probably heard, if they have ever read a single article about cosmology dozens of times. DESI, working slowly through millions of redshifts, has begun to suggest that this ending might not be what the universe is going to do. It might do something else. It might slow down. It might stop. It might, on a timescale of order 100 billion years, come back. The data is not conclusive. Nobody in the DESI collaboration is saying the universe is going to recollapse. The statistical significance of the result is below the threshold that physics treats as discovery. Several independent reanalyses have argued the signal is fragile, but the direction of the data, in 2 independent data releases now, is the same. And the direction is one that, for the first time in 27 years, refuses to rule out the oldest dismissed ending in cosmology. Tonight, while you settle in to listen to this, the 4-meter Mail telescope is open. The dome is rotating slowly to track the celestial sphere. The fiber positioners are reseating themselves in their patient, near-silent way. The data, in chunks of about 20,000 spectra per night, is flowing into the storage system at the National Optical Infrared Astronomy Research Laboratory. The 3rd data release is being prepared. And the question that Telescope is in the process of deciding, without making any announcement about it, is whether the universe expands forever, whether it slows and coasts, or whether it does the thing it was never supposed to do again. Whether it stops. What happens when it stops? That is the question this video is for. It is the question that physics had buried, and that the data has, against everyone's expectations, started to dig back up. To understand why DESI matters, you have to understand what the telescope is actually doing. The redshifts it measures are precise enough to be treated as a standard ruler. The ruler is the baryon acoustic oscillation scale, a feature in the galaxy distribution at a comoving size of about 150 megaparsecs. It is a frozen echo of pressure waves that propagated through the hot plasma of the early universe before recombination, when matter and radiation were coupled tightly enough that sound waves could move through them at relativistic speeds. When recombination happened, those sound waves froze in place. Every measurement of the BAO scale at a different redshift is a measurement of how much the universe has expanded since the light from that redshift left its source. The ruler stretches. The ratio of the ruler's apparent size to its true size tells you the expansion history. DESI is measuring that ratio at 7 different redshift bins, from about Z equals 0.3 out to about Z equals 2.3, with a separate measurement from the Lyman alpha forest of distant quasars at Z around 2.4. That gives the survey something no previous instrument has had: a continuous expansion history measurement spanning the past 10 billion years, with statistical weight large enough to detect deviations from the simplest cosmological model at the level of 1% or 2. The simplest model is called lambda cold dark matter. It is the 6-parameter model that has been the working assumption of professional cosmology for the last 25 years. The universe is flat. It is made of matter, including the cold dark matter that surrounds galaxies. It contains a cosmological constant, a uniform energy density of empty space, denoted with the Greek letter lambda. The value of lambda is fixed. It is, in the simplest reading, a property of the vacuum itself. In that model, the future is uneventful. Dark energy, in the form of lambda, dominates the energy budget today and will dominate it forever. The expansion rate will approach a constant value. The universe will enter an exponentially expanding de Sitter phase. Galaxies outside the local group will cross the cosmic event horizon, currently at about 16.6 billion light-years, and pass forever out of reach. The extragalactic sky will go dark, slowly, over the next 100 billion years. Stars will eventually exhaust their fuel. The stelliferous era will end around 10 to the 14th years. The degenerate era will follow, then the black hole era, then the dark era. The universe will end as it began, in something close to uniformity, except that the uniformity at the beginning was at maximum temperature and the uniformity at the end is at minimum. That is the textbook ending. And what DESI has begun to suggest, slowly and with the kind of careful hedging that the physics community uses when it does not want to overcommit, is that this ending is not guaranteed. The ambient sound in the dome on Kitt Peak tonight is mostly mechanical, the cooling pumps, the wind against the slit in the dome, the faint click of fiber positioners reseating. The data is not analyzed in real time. It is compressed, packaged, and shipped down the mountain at dawn. The analysis happens later, in offices at Berkeley and Stanford and a dozen other institutions, where the DESI collaboration is spread across roughly 900 individual physicists. The instrument is measuring redshifts while you listen to this. By morning, it will have added another 20,000 spectra to the largest cosmological map in human history. And what it is asking, with each one of those measurements, is whether dark energy is doing what we have been assuming it does. Whether the cosmological constant is, in fact, constant. Whether the value of lambda might be drifting in the decimals, in a way that nobody noticed for 27 years, because the older surveys did not have the statistical weight to see it. The data so far says, maybe. The data so far says, there is a preference, in our analysis, for a model where dark energy evolves. The data so far says, we cannot rule out the cosmological constant, but we cannot rule out evolution either, and the central values we are getting point in a specific, theoretically uncomfortable direction. The theoretically uncomfortable direction, decoded into the framing this video is going to spend the next 2 hours unpacking, is this. Dark energy might be weakening. The cosmological constant-like push that drove the discovery of cosmic acceleration in 1998 might not stay at the value it currently has. It might slowly decay. And if it decays far enough, and if it crosses through zero into negative values, the universe stops expanding and begins to contract. That is not a sentence physics had been saying in 2023. It is a sentence the data has begun to permit. It is a sentence that the DESI collaboration itself does not endorse. But it is a sentence that the most natural extrapolation of their two-parameter fit, taken at face value, requires. What happens when it stops? The question is not yet a measurement. It is, for the first time in 27 years, a question the data is no longer refusing to entertain. In the next 11 parts, we are going to walk slowly through what is at stake, back to 1922, and Friedmann's three solutions. Through the mid-20th century, when the big crunch was the leading expectation, into 1998, when the case was professionally closed, and through the math of what dark energy decay would mean and what the universe would look like, from inside, if it really did stop. What happens when it stops? Part 2. The first crack DESI data release 1. The first data release from DESI came out in April of 2024. The headline papers were posted to the Arxiv preprint server on the 3rd of April. The collaboration had been preparing for the release for more than a year. The actual analysis included data collected through about June of 2023. The galaxy and quasar samples covered an effective volume of roughly 30 billion cubic megaparsecs. To put that volume in human terms, it is a cube about 3 billion light-years on each side, and inside that cube, DESI had measured the redshifts of about 6 million individual galaxies and quasars, each one a point in a three-dimensional map of how matter is distributed across cosmic time. The analysis the collaboration ran on that data was, at the highest level, a careful comparison of two cosmological models. The first model was the standard one, lambda cold dark matter, with the cosmological constant fixed at exactly its observationally measured value and the equation of state of dark energy held at exactly -1. The second model was a more flexible one, in which the equation of state was allowed to vary across cosmic history. The parameterization used was one that has been standard in cosmology since the early 2000s. It is called the Chevalier-Pulaski-Linde parameterization, or CPL for short. It is a two-parameter fit in which the equation of state of dark energy is written as W of A equals W naught plus WA times the quantity 1 minus A, where A is the scale factor of the universe, a measure of how much the universe has expanded relative to today. The parameters W naught and WA are the two numbers the analysis is solving for. In a pure cosmological constant universe, W naught equals exactly -1 and WA equals exactly 0. A signal of evolution would be a measurement that excludes that point in the two-parameter plane. The DESI DR1 analysis combined the baryon acoustic oscillation measurements from DESI itself with the cosmic microwave background measurements from the Planck satellite's 2018 data release, with the addition of one of three different supernova samples Pantheon Plus, Union 3, or the Dark Energy Survey Year 5 sample. The result, in each case, was a preference for evolution. With Pantheon Plus, the best fit central values were W naught around -0.73, WA around -1.05. The exclusion of the cosmological constant point was at about 2.5 standard deviations. With Union 3, the same direction, slightly stronger, about 3.3 sigma. With the DES Year 5 sample, the same direction again, stronger still, about 3.9 sigma. Across all three combinations, the data preferred a model in which dark energy had been more like a cosmological constant in the distant past, and had been weakening since some moment in the relatively recent cosmic past, on the order of redshift 1 or so. There is a feature in those numbers that requires some unpacking, because it is the feature that drove most of the theoretical attention in the year that followed. Look at the central values. W naught around -0.73, WA around -1.05. Add them together. The sum is around -1.78. That sum, at redshift 0, gives the value of W today, which is roughly -0.73 in the DR1 fit. But if you extrapolate the model backward in cosmic time, to small values of the scale factor A, the value of W in the past was different. In the limit, A goes to 0, meaning the very early universe W went to W naught plus WA, which is -1.78. -1.78 is, in cosmology terms, deep in the phantom regime. The phantom regime is the range of values of W that lie below -1. Caldwell, Kamionkowski, and Weinberg gave the regime its name in a 2003 paper in Physical Review Letters, volume 91, page 07, 1301. They titled the paper Phantom Energy and Cosmic Doomsday. The reason for the title was that, if dark energy ever has W less than -1, the equation of state of the universe implies an end state in which all gravitationally bound structures are torn apart in finite time. Galaxies, solar systems, planets, eventually atoms. The end state of that scenario is called the Big Rip, and it is one of the more dramatic possible endings of the universe. The DR1 data did not say the universe is heading for a big rip. The DR1 data said something stranger. It said the universe might have been in the phantom regime in the past and might be heading away from it now. The technical name for that pattern is phantom, crossing the equation of state crosses the line W equals -1 at some point in cosmic history. Crossing the phantom line in either direction is theoretically uncomfortable. A canonical scalar field, meaning a scalar field with the simplest possible kinetic term in its Lagrangian, cannot have W less than -1 without becoming unstable. The proof of this is a relatively old result in field theory, and it has held up under decades of attempts to find loopholes. If the universe really did cross the phantom line, then dark energy is not a single canonical scalar field. It is something more elaborate. The DESI collaboration in the DR1 paper did not dwell on the phantom crossing. They simply reported the central values, the statistical significance, and the consistency with the data. They did not endorse evolving dark energy as a discovery. They used the word preference. The DR1 result is consistent with the cosmological constant at, depending on the sample, between 2.5 and 4 standard deviations. That is not a discovery. That is, in cosmology terms, a tantalizing hint. But it is a hint that pointed in a particular direction, and that direction was the direction physics had not been entertaining seriously for 25 years. In the weeks after the release, the physics community responded in approximately the way it always responds to a tantalizing but not conclusive result. There were follow-up theoretical papers. There were reanalyses by external groups. There were arguments about which supernova sample was the most trustworthy. There were proposals for new models that could naturally produce a phantom crossing quintessence plus k-essence, two field combinations, interacting dark energy models in which the dark sector exchanges energy with cold dark matter, early dark energy models that turn off after recombination, and a handful of more exotic possibilities. Most of these models were not new. They had been sitting in the theoretical cosmology toolkit for years, in the back pocket of the field, waiting for a data signal that might require them. The DR1 result was the first signal that might. There was also a quieter conversation, mostly happening at conferences and in seminar Q&A sessions, about what the trend implied for the universe's future. If dark energy was weakening, what did that mean for the asymptotic accelerating de Sitter ending? If the universe had spent some time in the phantom regime and had now exited it, what was the trend going to do next? Was the equation of state going to keep drifting toward less negative values? Was it going to stabilize? Was it going to cross zero? The cleanest extrapolation of the CPL fit, taken absolutely at face value, predicted that the equation of state would, in the future, continue to evolve along the linear in a trajectory the parameterization implied. That meant that, depending on the steepness of WA, dark energy might eventually approach zero on a timescale of order tens of billions of years. That extrapolation is the one that put the big crunch back on the conversation, even before DR2 came out. Several theoretical papers, in mid-2024, most prominently Adil, Mukherjee, and Sen, in RxIve preprint 2404.10197, showed that if you took the DR1 central values seriously and extrapolated them forward, the universe would, under specific assumptions about how the trend continued, recollapse on a timescale of about 30 to 50 billion years. That paper, and others like it that followed in the next few months, were not predictions, they were existence proofs. They demonstrated that the DR1 fit was compatible, mathematically, with a universe that recollapses. They did not claim recollapse was the most likely future. They claimed that the data, as published, did not exclude recollapse, and that the central values pointed in a direction consistent with it. This was the first crack in the textbook ending. It was, in 2024, a small crack. The result was preliminary. The statistical significance was below the discovery threshold. The extrapolations relied on a specific functional form for W of A, and that form was not guaranteed to capture the true behavior of dark energy in the future. But the crack was real, and the people who were closest to the data were the people who took it most seriously. By the summer of 2024, the phrase evolving dark energy was no longer a niche theoretical proposal. It was something the working cosmology community was treating as a live possibility. The DESI collaboration spent the rest of 2024 collecting more data. The fiber positioners on the Male telescope continued their nightly work, reseating, recording, reseating. The data accumulated. The third year of survey time was completed in the summer of 2024. The analysis pipeline was tuned, validated against the DR1 sample, and prepared for the next major release. The community waited. What the DR1 result had really done was set a question. The DR1 question was simple. If we triple the data, does the signal hold up? The answer to that question came in March of 2025. Part 3. The crack widens. DESI Data Release 2. The American Physical Society's annual Global Summit in 2025 was held in Anaheim, California, from the 15th to the 19th of March. The DESI collaboration had announced, weeks in advance, that they would present updated cosmological constraints on the 19th, the final day of the meeting. The room was full. The talk was given by one of the lead analysis coordinators. The slides moved through the survey statistics first, about 14 million galaxies and quasars measured, about 3 years of survey time accumulated, BAO measurements at 7 effective redshift bins covering the range from Z equals 0.3 to Z above 2. Then the slides moved to the cosmological constraints. The pattern from DR1 was holding up. The fit to the CPL parameterization, with the same combinations of BAO, CMB, and supernova samples, was still preferring evolving dark energy. The central values had shifted slightly. They had not collapsed back toward the cosmological constant point. The statistical significance was, in the strongest combination, slightly higher than DR1, in the weakest combination, slightly lower. But the direction of the preference was the same. The headline numbers from the DR2 paper, posted to the archive as preprint 2504.14005 in April of 2025, were these. The central value of W0, the equation of state today, was approximately negative 0.83, with a 1 sigma uncertainty of about 0.058. The central value of WA, the rate of evolution, was approximately negative 0.75, with a 1 sigma uncertainty of about 0.25. The combined preference for evolving dark energy over the cosmological constant, depending on the supernova sample, ran between 2.8 and 4.2 standard deviations. With the Pantheon Plus sample, about 3.1 sigma. With the DESI 5 sample, about 4.2 sigma. With Union 3, intermediate. Those numbers describe a particular shape of dark energy history. Dark energy today is acting close to a cosmological constant, but slightly less negative W, around negative 0.83, instead of exactly negative 1. In the past, dark energy was acting more like a constant closer to W equals negative 1, and it was even, briefly, in the phantom regime, with W less than negative 1. The crossing of the phantom line occurred somewhere around redshift 1 or so, when the universe was about half its present age. Since then, dark energy has been weakening. The trend, extrapolated forward, has it continuing to weaken. It is worth pausing on what those numbers actually permit. The DR2 central values, taken at face value, and extrapolated linearly into the future using the CPL parameterization, predict that the equation of state of dark energy will cross zero at some moment several tens of billions of years from now. The crossing of zero is the threshold for recollapse. If W crosses zero and becomes positive, the dark energy term in the Friedmann equation flips from a force that drives expansion to a force that opposes it. The expansion of the universe, which has been accelerating for about 6 billion years, slows down. The Hubble parameter, which is currently positive and slowly decreasing, would continue to decrease. At some moment, it would pass through zero. The universe would stop expanding. And then, with the dark energy term continuing to grow as a decelerator, the universe would begin to contract. The precise timescale for this scenario depends on assumptions about how the CPL extrapolation continues past the data window. The DR2 data only constrains the equation of state from the present back to redshift 2 or so. It does not directly constrain the value of W in the future. The extrapolation is a model assumption. If you assume the CPL parameterization remains valid into the future, you get one set of timescales. If you assume dark energy might saturate at some asymptotic value, or oscillate, or undergo a more complicated evolution, you get different timescales, possibly no recollapse at all. The simplest extrapolations, using the DR2 central values, give recollapse timescales in the range of 30 to 100 billion years. The wide range reflects the freedom in how aggressively the CPL parameterization is extended past the data. The smaller end of the range is from extrapolations that assume the linear in A evolution continues uninterrupted. The larger end of the range is from extrapolations that allow some slowing of the evolution, but assume the eventual sign change of dark energy is real. For context, the universe is currently about 13.8 billion years old. The Sun has about 5 billion years left as a main sequence star. The Andromeda Galaxy will collide with the Milky Way in about 4.5 billion years. The Earth will be engulfed by the Sun's red giant phase in about 7.6 billion years, according to the Schroeder and Conan-Smith analysis published in monthly notices of the Royal Astronomical Society in 2008. A recollapse on the timescale of 30 to 100 billion years is, in human terms, unimaginably distant. It is, in cosmic terms, the same order of magnitude as the time the universe has already lived. The recollapse, if it is real, is something the universe is just about halfway through having not yet done. The careful language used by the DESI collaboration about the DR2 result is important. The collaboration did not claim a discovery. They used the word preference in their abstract. They noted that the statistical significance was sample-dependent. They emphasized that BAO data alone, without combining with a supernova sample, was consistent with the cosmological constant at between 1.3 and 1.9 sigma, meaning the entire evolving dark energy signal in the DESI analysis depended on the supernova sample to break the degeneracy between the matter density and the dark energy evolution. The signal was not in DESI data alone. It was in DESI data combined with one of several supernova samples whose systematics are still being worked through. That careful framing matters because it places the result in a specific epistemic category. It is not a discovery. It is not a fluctuation that the collaboration is dismissing. It is a preference in a particular fit that the collaboration is reporting as scientifically interesting but not yet binding. It is something the field is meant to test against the next generation of data, with the next generation of surveys, with the next generation of supernova samples, with the next generation of theoretical interpretation. The path from a 3 sigma preference to a 5 sigma discovery in cosmology often takes a decade. Sometimes it never closes. The DR2 result is, as of 2026, on that path. It has not arrived. But what makes the DR2 result interesting, structurally, is that it is consistent with DR1. The two analyses are not independent. They share most of their data, but DR2 uses substantially more BAO weight than DR1 did. If the DR1 result had been a statistical fluctuation, DR2 should have moved the central values back toward the cosmological constant point. They did not. They moved sideways, slightly. They held the direction of the DR1 preference. The fluctuation interpretation is now harder to sustain than it was in 2024. Not impossible, just harder. External reanalyses of the DR2 result have been mixed. Cortes and Liddell, in RxIve preprint 2408.10503 from August of 2024, ran an independent reanalysis of the DR1 sample and recovered central values very close to the DESI author's preferred ones. Subsequent reanalyses in 2025 have confirmed similar agreement with DR2. On the other hand, several papers, including a series from the Colgine Group at Sungkyunkwan University in Korea, have argued that the apparent evolution is sensitive to a single high redshift BAO point, measured from the Lyman alpha forest of distant quasars. Removing or downweighting that single point reduces the significance of the evolving W signal noticeably. The argument is not that the DESI authors did anything wrong. The argument is that the result depends, more than is comfortable, on the high Z BAO point, and that the systematic uncertainties at that redshift may not be fully under control. The supernova sample dependence is the other piece of structural fragility in the DR2 result. The three samples, Pantheon Plus, Union 3, and DES Year 5, disagree with each other at the level of 1 or 2 sigma in their preferred cosmological parameters, even before combining with DESI. The Pantheon Plus sample is the largest and most carefully calibrated, but it has known systematic issues at the high redshift end. The DES Year 5 sample, which gives the highest DESI combined significance, is internally homogeneous in a way Pantheon Plus is not, but it covers a smaller redshift range. The Union 3 sample is a compromise. Pippin et al., in a series of papers in 2025, have argued that the DE's Year 5 sample has a specific calibration issue at the high redshift end that, when corrected, slightly weakens the evolving W signal. The DESI authors are aware of these issues. The DR2 paper discusses them explicitly. The DR2 result is therefore not the kind of result that gets confirmed or refuted in a single follow-up paper. It is the kind of result that the field will spend years untangling. But the direction of the result is real. The direction is the direction. After 2 independent data releases now, the preference is for evolving dark energy with a phantom crossing in the past and a trajectory that, if extrapolated, leads to a slowing acceleration and possibly a recollapse. The textbook ending is, in the most literal sense, no longer guaranteed by the data. It is one possible ending out of a small family of plausible endings, and which one is correct depends on numbers that are not yet pinned to the precision required to decide. The DR2 release in March 2025 was followed by a year of theoretical activity. New models were proposed. Existing models were refined. The Cosmology RxIV averaged several dozen papers a month on the implications of the DESI results through 2025 and into early 2026. Most of the papers, taken together, said the same thing. The data is interesting, the theoretical models are increasingly elaborate, and the discovery threshold has not yet been crossed. What the field is now waiting for is the next data release. DR3 is expected sometime in 2026 or 2027. The Euclid satellite, launched by the European Space Agency in 2023, is producing its own BAO measurements that will be combined with DESI in joint analyses. The Vera Rubin Observatory in Chile, currently entering its survey phase, will produce a supernova sample many times the size of any existing one. The Roman Space Telescope, scheduled for launch in 2027, will add infrared BAO and supernova measurements. Within 5 to 10 years, the precision on W0 and WA will improve by a factor of 2 or 3. The 5 sigma discovery threshold will either be crossed or the signal will fade. For now, the result is a preference, and the universe's ending is, for the first time in 27 years, an open question. Part 4. The implication nobody quite voiced. There is a kind of result in physics that the press releases do not quite want to spell out. The DR1 paper said dark energy might be evolving. The DR2 paper said dark energy might be evolving more confidently. Neither paper said what an extrapolated time-varying dark energy actually implies for the future of everything. That second sentence was left, in both cases, for the theoretical follow-up papers, which arrived in the months after each release in waves of arXiv preprints. The reason for the omission is not mysterious. Saying dark energy might be evolving is a careful, precise, scientific statement consistent with the data. Saying the universe might stop expanding is, even though it is the same statement reread in different language, a sentence that sounds less like science and more like a news headline. The DESI authors are professionals. They do not want their result confused with a horror movie, but the implication is in the data. The implication is built into the parameterization. If W0 is around negative 0.8 and WA is around negative 0.75, and if the CPL form is taken seriously into the future, then the equation of state of dark energy is approaching zero from below. The current value of dark energy density is positive. The current value of W is negative. The product of those, which is what enters the deceleration parameter of the Friedmann equation, is currently the term that drives accelerating expansion. If W continues to drift upward towards zero, the magnitude of that driving term decreases. The acceleration slows. If W eventually crosses zero into positive values, the dark energy term becomes a decelerator rather than an accelerator. Combined with the always decelerating matter term, the universe stops expanding. The Hubble parameter goes through zero. The universe begins to contract. That sequence of events is not unique to the CPL parameterization. It is the generic behavior of any model in which dark energy is decaying towards zero from positive values. It does not require dark energy to actually become negative. It only requires the effective contribution of dark energy to the Friedmann equation to fall below the contribution that matter would have made on its own. In a universe with omega m around 0.3 and the cosmological constant in its standard form, the cosmological constant always wins eventually because it does not dilute. In a universe with evolving dark energy, that is no longer guaranteed. Matter dilutes as the universe expands, but if dark energy dilutes faster, or, more strikingly, decays to zero or below, then matter is allowed to win again. The class of models in which dark energy actually goes negative, meaning the dark energy density itself flips sign, becoming a small, negative, effective contribution to the Friedmann equation, is the class that produces a hard, big crunch. In those models, the universe stops expanding, begins to contract, and the contraction accelerates as the negative dark energy term grows in magnitude. Adil, Mukherjee, and Sen, in their April 2024 paper, worked out the cosmological consequences of one such negative dark energy scenario in detail. They found that scenarios consistent with the DESI bow data predicted recollapse on timescales of about 30 to 100 billion years, with the precise number depending on how aggressively they allowed the dark energy evolution to proceed past the data window. The DESI result, by itself, does not require dark energy to become negative. It only requires dark energy to evolve. The CPL parameterization, extrapolated into the future, gives a range of behaviors, of which only the more extreme ones lead to negative effective dark energy. The more moderate extrapolations give an asymptotic coast scenario, in which dark energy decays towards zero but does not cross it, and the universe enters a steady-state expansion that neither accelerates nor decelerates. That scenario does not produce a big crunch. It produces a quieter ending. The universe simply stops accelerating, the cosmic event horizon stabilizes, and matter dilutes to nothing on a timescale that, while long, is at least finite. The asymptotic coast is the least dramatic possible reading of the DESI result. It is also, in many ways, the most boring possible ending of the universe. Between the textbook accelerating de Sitter ending and the new dark energy decay endings, the universe's fate now lives in a broader space than it did before 2024. There is the original lambda cold dark matter ending, in which dark energy is exactly constant and the universe expands forever. There is the asymptotic coast, in which dark energy decays towards zero but does not cross it. There is the soft, big crunch, in which dark energy crosses zero into negative values and the universe recollapses on a timescale of order 100 billion years. There is the hard, big crunch, in which the recollapse continues all the way to a singularity and the universe ends in mathematics that breaks down. There is the bounce, in which the singularity is smoothed out by quantum gravity effects and the universe rebounds into a new, expanding phase. And there is the cyclic, in which a chain of expansions and contractions runs indefinitely. 2 years ago, that list of possible endings was a textbook exercise. The accelerating de Sitter ending had been the working assumption for a quarter century. The other endings were treated as fringe possibilities, theoretical curiosities, alternatives that physics had moved past. The DESI result has not made any of those other endings likely. It has only made them, for the first time in decades, no longer ruled out. That is the implication nobody quite voiced. The textbook ending is not guaranteed. It is one possible ending among several. And the data, slowly and against expectation, has begun to permit endings the field had professionally retired. There is a useful frame for thinking about this. Cosmology spent the second half of the 20th century narrowing the field of possible universes. The discovery of the cosmic microwave background in 1964 ruled out the steady-state model. The observation of cosmic structure ruled out the topological defect models. The measurements of the matter density ruled out the closed recollapsing models. The discovery of acceleration in 1998 introduced the cosmological constant. The Planck measurements through the 2010s narrowed the parameter space of lambda cold dark matter to remarkable precision. By 2020, the model had 6 parameters, all of which were measured to better than a few percent. The universe, by the working assumption of the field, was a fully determined system. Its past was reconstructed, its present was measured, its future was extrapolated. The DESI result is the first measurement in a generation that has widened the parameter space rather than narrowing it. The result is consistent with the cosmological constant, but it is also consistent with a class of evolving dark energy models that produce qualitatively different futures. The standard model is still one of the allowed scenarios, but it is no longer the only one. The field has, after 25 years of narrowing, widened. What that means, structurally, is that the universe's ending is, for the first time in a generation, an open question that the data has actively reopened. It is not an open question because someone decided to revisit an old debate. It is an open question because the measurements have, against the expectations of the people taking the measurements, refused to converge on the simplest answer. Several alternative endings are now living, again, in the space of plausible futures. The big crunch is one of them, the asymptotic coast is another, the bounce is a third. Which one we live in depends on numbers that the next generation of surveys will measure with 2 or 3 times the precision of the current ones, and that may or may not converge cleanly to a single answer even then. There is one more piece of context that matters here. The Hubble tension has been a separate, parallel anomaly in cosmology for about a decade. The Planck-derived Hubble constant of 67.4 kilometers per second per megaparsec disagrees with the local distance ladder Hubble constant from the SH0ES team measured at 73.04, with a 1 sigma uncertainty of 1.04. The disagreement is at about 5 standard deviations. It has not budged with more data. It is generally treated by the field as the most direct evidence that the standard cosmological model is incomplete, that something is missing from the physics between recombination, where Planck makes its measurement, and the present epoch, where SH0ES makes its measurement. The Hubble tension and the DESI evolving W preference may be connected. Several papers in 2025 have argued that the same modifications to the standard model that produce the DESI signal also reduce or eliminate the Hubble tension. The class of models doing the work is the class of models in which the dark sector, dark energy, and dark matter together has structure beyond what the 6-parameter lambda cold dark matter model assumes. Models with interacting dark energy, early dark energy, or sector-crossing interactions can address both anomalies at once. The fact that 2 independent tensions point in compatible directions is taken by people who take it seriously as a sign that the standard model is not just being statistically unlucky in 2 places. It is missing physics in both places, and the missing physics may be the same physics in both cases. That is the structural backdrop against which the big crunch question now sits. It is not just that one survey has produced a tantalizing result. It is that the field has been accumulating, for about a decade, signs that the simplest cosmological model does not fully describe the universe. The Hubble tension was the first sign. The DESI evolving W preference is the second. The connection between them, if it is real, points at a modification of dark energy itself. And modifications of dark energy are exactly the kind of physics that determine whether the universe expands forever or eventually stops. The textbook ending is not guaranteed. It has not been ruled out. But for the first time in a quarter century, neither has the recollapse, neither has the bounce, neither has the cyclic. The field has re-entered, against its own expectations, an era in which more than one ending of the universe is on the table. To understand how we got here, how a question that was professionally retired in 1998 could be reopened by a single survey 27 years later, we have to go back further than the discovery of acceleration. We have to go back to 1922, to a paper by a Soviet meteorologist named Alexander Friedmann, who took Einstein's field equations and wrote out the 3 possible futures of the universe for the first time. That is the next part of this video. Part 5. Friedmann's 3 solutions. In 1922, a Soviet meteorologist named Alexander Friedmann sat down with Einstein's general theory of relativity and did something that, at the time, almost no one else had thought to do. He took the field equations of general relativity, applied them to the universe as a whole, and asked what kinds of cosmic geometries the equations actually permitted. Einstein himself had assumed, in his 1917 cosmological paper, that the universe was static, that it was neither expanding nor contracting, but sitting in a steady, eternal balance. To make that work, Einstein had introduced a term into his equations that he called the cosmological constant, which he labelled with the Greek letter lambda. The lambda term provided the small outward pressure necessary to balance against gravity and keep the universe from collapsing under its own weight. Einstein, looking at his equations, had been bothered by the fact that without lambda, the equations did not naturally produce a static universe. They produced something that was either expanding or contracting. Einstein, who like everyone else in 1917 assumed the universe was static, treated this as a problem with the equations rather than a feature of reality. Friedmann did not share that assumption. He was a mathematician by training, working as a meteorologist in Petrograd, which had been St. Petersburg before the revolution and would become Leningrad after Lenin's death. He was 34 years old. He had a wife and a young son. He was working in what was, in 1922, a country in the middle of post-revolutionary economic collapse, in a city where intellectual life persisted in cold apartments and underfunded institutes. He published his paper in the German journal Zeitschrift für Physik in volume 10, page 377. The title, translated, was On the Curvature of Space. What Friedmann did in that paper was treat the universe as a uniform, isotropic fluid with some matter density and some curvature, and solve Einstein's field equations for the resulting cosmological geometry. The solutions he found came in three families, distinguished by the sign of the spatial curvature parameter. He called the parameter k. If k was positive, the universe had the spatial geometry of a three-dimensional sphere, finite but unbounded, closed in on itself. If k was 0, the spatial geometry was flat three-dimensional Euclidean space, infinite in extent, the geometry of the ordinary intuition. If k was negative, the spatial geometry was hyperbolic, the three-dimensional generalization of a saddle, also infinite, but curving outward rather than inward. For each of these three geometries, Friedmann's equations predicted a different dynamical behavior. The flat universe and the open universe k equal to 0 and k negative would both expand forever, with the expansion rate slowing asymptotically towards 0 in the flat case and towards some constant in the open case. The closed universe k positive would expand for some finite time, then stop, then begin to contract, then collapse on itself in a singularity that mirrored the initial moment of the expansion. That third solution, the closed universe recollapse, was the first time in the history of physics that anyone had written down, mathematically, the possibility that the universe might end. The mathematics was simple. The geometry was the geometry of a three-sphere, the three-dimensional analogue of the two-dimensional surface of a balloon. The universe expanded outward, reached a maximum scale, and then contracted back toward a final point. The ending was as inevitable, in the closed universe case, as the beginning had been. It was a feature of the geometry. It was, in Friedmann's words, the natural consequence of taking general relativity seriously and asking what kind of universe it predicted. Einstein read the paper. He did not like it. He sent a short, dismissive reply to Zeitschrift für Physik in the next issue, claiming that Friedmann had made a mathematical error. Friedmann, when he received Einstein's reply, was upset. He wrote back, carefully, explaining where Einstein had misread the algebra. He sent the explanation through a colleague who was travelling to Berlin. Einstein, eventually, conceded. He published a second short note in 1923, retracting his criticism and acknowledging that Friedmann's mathematics was correct. The retraction was published more than a year after the original criticism. Friedmann never saw it widely circulated. He died in 1925 of typhoid fever, at the age of 37, before his work was widely accepted as the foundation it would later become. The three-phase framework that Friedmann produced is, in a real sense, the deepest mathematical structure of modern cosmology. Every cosmological model since has been an elaboration of one of his three solutions. The Big Bang model, originally proposed by Georges Lemaitre in 1927 and worked out in detail by Gamow, Alpha, and Hermann in the late 1940s, was a Friedmann universe with specific initial conditions. The steady-state model, proposed by Hoyle, Bondi, and Gold in 1948, was an attempt to avoid Friedmann's framework by introducing continuous creation of matter. The inflationary models of the 1980s were Friedmann universes with an additional, very early universe phase. The current lambda cold dark matter model is a Friedmann universe with the cosmological constant restored. Each generation of cosmology has refined the framework, added components, measured the parameters more precisely, but the framework itself, the three solutions, and their consequences, has remained Friedmann's. What Friedmann did not have, and could not have had, in 1922 was data. There were no measurements of cosmic expansion. There were no observations of distant galaxies as systems beyond the Milky Way. The very fact that other galaxies existed had only been established by Edwin Hubble's 1924 observations of Cepheid variable stars in the Andromeda Nebula, 2 years after Friedmann's paper. There was no cosmological data, in any meaningful sense, in 1922. Friedmann's framework was pure mathematics, 3 solutions to the equations, with no empirical basis for choosing among them. The empirical basis came over the following decade. Hubble's 1929 paper, in the Proceedings of the National Academy of Sciences, Volume 15, page 168, established that the redshifts of distant galaxies were linearly proportional to their distances. The universe, it turned out, was expanding. Lemaitre's 1927 paper had already proposed the same thing on theoretical grounds, with a different interpretation of his own data. The interpretation of the observed expansion as a universal recession of galaxies, consistent with Friedmann's mathematics, was settled by the early 1930s. The question shifted from whether the universe was expanding to which of Friedmann's 3 solutions it was following, and that question came down to the value of the cosmic matter density. The Friedmann equations make the question explicit. In the flat universe case, k equals 0, the matter density takes a specific value called the critical density. The critical density is ρc equals 3h squared divided by 8 pi g, where h is the Hubble parameter and g is Newton's gravitational constant. At today's Hubble parameter of about 67 kilometers per second per megaparsec, the critical density works out to about 9.47 times 10 to the negative 27th kilograms per cubic meter. That is about 5 or 6 hydrogen atoms per cubic meter averaged over the volume of the universe. If the actual matter density of the universe is exactly the critical density, the universe is flat and expands forever at a decelerating rate that asymptotes to 0. If the actual density is greater than critical, the universe is closed and eventually recollapses. If the actual density is less than critical, the universe is open and expands forever at a decelerating rate that asymptotes to a positive value. The fate of the universe, in Friedmann's framework without a cosmological constant, comes down to a single number, the ratio of the actual matter density to the critical density, which cosmologists call omega m, the matter density parameter. For omega m equals 1, exactly, the universe is flat. For omega m greater than 1, the universe recollapses. For omega m less than 1, the universe expands forever. The number is, in some sense, the most consequential number in cosmology. It decides whether the universe ends in heat death or in a big crunch. It decides whether the universe is finite or infinite. It decides what kind of geometry the universe has. For most of the 20th century, measuring omega m precisely was the central observational problem of cosmology. The measurements came in slowly, with substantial uncertainties, from a variety of techniques. The mass-to-light ratios of galaxy clusters, the dynamics of galaxy rotation curves, the large-scale structure surveys of the 1970s and 80s, the X-ray emission from intracluster gas. Each technique had its own systematics and its own bias. But by the early 1990s, a rough consensus had emerged. The matter density of the universe was around omega m equals 0.2 to 0.3, with significant uncertainties in either direction. The universe, in other words, was open. The matter density was less than critical. Friedmann's third solution, the closed universe recollapse, was not the one we lived in. That conclusion, however, sat uneasily with another piece of theoretical cosmology that had been gaining ground since the early 1980s inflation. The inflationary model, proposed by Alan Guth in his 1981 paper in Physical Review D, Volume 23, page 347, posited a brief period of exponential expansion in the very early universe that would, as a generic feature, drive the spatial curvature toward exactly zero. Inflation's prediction was a flat universe, omega total equals 1. The matter measurements gave omega m around 0.3. The two numbers did not agree. Through the 1990s, this tension was one of the central problems in observational cosmology. Either inflation was wrong, or the matter density was higher than the measurements suggested, or there was some additional component of the universe that contributed to omega total without being detected in mass-to-light measurements. The first option was theoretically uncomfortable inflation solved too many problems to be dismissed. The second option was empirically uncomfortable. The matter measurements were independent enough that hidden matter at the level needed to bring omega m to 1 was hard to accommodate. The third option, the missing component option, was the one that took longer to fully develop, but it was the one that, by the end of the 1990s, would be vindicated. That missing component was dark energy. The discovery of it, in 1998, would resolve the omega total problem in a single blow by introducing a uniform energy density of empty space that contributed roughly 0.7 of the critical density, bringing the total to exactly 1, satisfying inflation, and explaining why the matter measurements had always come up short. But it would also, in the same moment, change Friedmann's framework irrevocably. With a cosmological constant in place, the three-fate framework no longer applied straightforwardly. The geometry of the universe, by itself, no longer determined its future. The cosmological constant, if it stayed constant, guaranteed eternal accelerating expansion regardless of geometry. The closed universe recollapse was, in the new framework, ruled out not by the geometry, but by the dark energy. That is the framework physics has lived in since 1998. It is the framework DESI is now, slowly, testing the limits of, and it is the framework that, if dark energy is doing something other than staying constant, might no longer fully apply. Friedmann's three solutions are still there. They have been augmented, but they have not been replaced. The recollapse is one of them. It has been pushed to the back of the menu. It has not been removed. The data of the next decade will decide whether it stays there or whether it returns. Part 6. The decades the Big Crunch was alive. For most of the middle of the 20th century, the recollapse was not a fringe scenario, it was the leading scenario. The textbook image of the universe that students learned, in courses taught from the 1960s through the late 1980s, was an image of a universe that had been expanding from a hot, dense initial state, was still expanding now, and would eventually stop expanding and recollapse. The Big Crunch was the default. It was not the unlikely outcome that physics had grudgingly considered. It was the expected outcome that physics was, in the slow accumulation of mass measurements, trying to confirm. The reasons for the dominance of the recollapse scenario in mid-century cosmology were several. First, there was a general aesthetic preference for closed universe geometries. A closed universe is mathematically elegant. It is finite. It has a well-defined total mass and a well-defined total volume. It avoids the philosophical awkwardness of an infinite spatial extent. The flat universe and open universe geometries, by contrast, are spatially infinite, and a spatially infinite universe raises questions about boundary conditions, about the meaningfulness of total quantities, and about the relationship between local and global physics. Many mid-century cosmologists preferred, on aesthetic grounds, the closed universe option. Second, there was the empirical situation of the matter density. In the 1960s and 70s, the mass-to-light measurements of galaxy clusters were producing estimates of omega m that were highly uncertain but consistently below 1. The exact values varied. Some measurements gave omega m around 0.1. Others gave 0.3. Some, in particular clusters, gave values closer to 1. The error bars were large enough that the true value might plausibly have been anywhere from 0.05 to 2 or 3. The default working assumption, in the absence of a clear measurement, was that the unknown additional mass, the so-called dark matter, whose existence had been argued for by Zwicky in 1933 and by Rubin in the 1970s, would eventually bring omega up to a value at or near 1. In the closed universe limit, that would mean recollapse. Third, there was the conceptual framework of inflation, which arrived in 1981 and predicted a flat universe. Inflation made the natural value of omega total exactly 1. If omega m turned out to be less than 1, inflation would still allow the universe to be flat, but the missing density would have to come from somewhere. The leading candidate in the early 1980s was a hypothetical sea of cosmic strings or topological defects. The cosmological constant was not yet a serious contender. Einstein's original lambda was generally regarded, through the 1970s and 80s, as a failed proposal that had been retired when Hubble's expansion measurement showed the universe was not static. Fourth, there was the deceleration parameter. The deceleration parameter, traditionally written as Q0, is a single number that captures how much the expansion of the universe is slowing down. In a matter-dominated universe with no cosmological constant, Q0 is directly related to omega m. A Q0 greater than 0.5 means the matter density is above critical and the universe recollapses. A Q0 less than 0.5 means the universe is open and expands forever. A Q0 of exactly 0.5 means the universe is flat. In the 1960s, Alan Sandage at the Carnegie Observatories proposed that measuring Q0 precisely was the central observational task of cosmology. His 1961 paper in the Astrophysical Journal, Volume 133, page 355, titled "The Ability of the 200-inch Telescope to Discriminate Between Selected World Models," laid out the program. Measure Q0. Decide whether it is above 0.5 or below. The future of the universe recollapse or eternal expansion is determined by which side of 0.5 the universe sits on. The measurements of Q0 through the 1960s and 70s and 80s were, like the measurements of omega m, highly uncertain. The technique was to measure the apparent magnitudes of distant galaxies, usually the brightest galaxies in distant galaxy clusters, as standard candles and fit them against the various cosmological models. The measurements were difficult. The galaxies were dim. The standard candle assumption had to be corrected for evolution, since distant galaxies were younger than nearby ones. The corrections introduced systematic uncertainties that often exceeded the statistical ones. By the early 1990s, the Q0 measurements had not converged on a clear answer. The data tended to favor Q0 less than 0.5, meaning the universe was open and would not recollapse, but the uncertainties were large enough that the closed universe option was still alive. The Sandage program was a long-running, decades-spanning project that had not yet produced its decisive result. What sat in the background of all this was a particular intellectual structure. The closed recollapsing universe was, in some ways, the most narratively complete model of cosmology. It had a beginning, a middle, and an end. The Big Bang opened the story, the expansion played it out, the Big Crunch closed it. The universe was a finite event in a finite duration with a coherent dramatic arc. The open and flat models, by contrast, had a beginning but no ending. They trailed off into an asymptotic future of cold dilution that did not have the same narrative weight. The cosmologists who worked on these models in the middle decades of the 20th century knew, on some level, that the choice between the futures was an empirical question, not an aesthetic one. But the aesthetic preference for the closed recollapsing model was real, and it shaped the way the field was taught and the way the public received cosmology. The textbooks of the 1970s and 80s typically presented the three Friedmann solutions with roughly equal weight, but the closed recollapsing one was often given the most space and the most evocative diagrams. The image of the universe expanding to a maximum size, then contracting, then collapsing back to a singularity, was the iconic cosmological image of mid-century science. It was on Carl Sagan's Cosmos in 1980. It was in Steven Weinberg's First 3 Minutes in 1977. It was the picture, more or less, that most people had in mind when they thought about how the universe might end. That picture began to come apart slowly in the late 1980s, as the mass measurements continued to suggest omega m was firmly below 1. By the early 1990s, the open universe interpretation was the working assumption of most observational cosmologists, even as the inflation-based theorists continued to expect that the missing density would eventually turn up somewhere. The closed universe recollapse model was, by 1995, a minority position. It was not dead. It was, in the language of the field, becoming disfavored. What killed it definitively was not a measurement of omega m. It was a measurement of something else, the deceleration parameter, measured by a method that nobody in 1995 was confident could be made to work. The method was the use of type Ia supernovae as standard candles at cosmological distances. Two competing teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, had been working through the mid-1990s to push the supernova distance measurements out to redshifts where the difference between the various cosmological models would become detectable. The work was painstaking. The supernovae were rare. The corrections for evolution and reddening and host galaxy variation were difficult. The teams disagreed about each other's methods. The progress was slow. By the spring of 1998, both teams had accumulated enough supernovae at high redshift to start making the comparison with theory. And both teams, working independently, with different methods, with different supernova samples, found the same impossible thing. The high redshift supernovae were dimmer than any of the standard cosmological models predicted. They were dimmer in a way that was not consistent with Q0 greater than 0.5. They were not consistent with Q0 between 0 and 0.5. They were not consistent with Q0 equal to 0. They were consistent only with a value of Q0 that was negative, meaning the universe was not slowing down at all. It was, in defiance of every model that had been seriously considered, accelerating. The recollapse case did not die in a single moment. It died slowly, over the course of a few weeks in the spring of 1998, as the two teams independently checked their work, looked for errors, found none, and arrived at the same conclusion. The universe was not heading for a big crunch. It was not heading for a coasting infinite expansion either. It was accelerating, and the only natural explanation for the acceleration was a non-zero cosmological constant. That is the story of 1998, and it is what the next part of this video is about. Part 7. The year the case closed. The two teams that killed the Big Crunch in 1998 were not a coordinated effort. They were rivals. They had spent most of the 1990s competing for telescope time, for supernova candidates, for early publication, and for the credibility that comes with being first. The High-Z Supernova Search Team was led by Brian Schmidt and based at the Australian National University and Harvard. The Supernova Cosmology Project was led by Saul Perlmutter and based at Lawrence Berkeley National Laboratory. The two groups did not collaborate. They did not share data. They occasionally borrowed observing time from each other when scheduling permitted, but the work was, by design, independent. The independence is the reason the discovery, when it came, was credible. Two competing teams using different methods on different supernova samples, arriving at the same impossible result, is a much harder finding to dismiss than a single team's result on a single sample. The work began in earnest in the early 1990s. The technical challenge was to identify type Ia supernovae at redshifts high enough to discriminate between cosmological models. Type Ia supernovae are the thermonuclear explosions of white dwarf stars that have accumulated mass from a companion star past the Chandrasekhar limit of about 1.4 solar masses. They are useful as standard candles because, after a correction for the shape of the light curve, known as the stretch correction, their peak luminosities cluster around a narrow value with an intrinsic scatter of about 10 to 15%. That scatter is small enough that they can be used to measure distances at the cosmological scale, where the differences between cosmological models become significant. The technical problem was finding them. Type Ia supernovae are rare. In a typical large galaxy, one occurs roughly every few hundred years. Finding one at high redshift requires monitoring a large patch of sky and looking for transient events that brighten and then fade on a timescale of weeks. The standard method, developed through the early 1990s by both teams, was to take wide-field images of the same patch of sky at multiple epochs, then digitally subtract the earlier image from the later one to reveal transient sources. The transients then had to be followed up spectroscopically with larger telescopes to confirm the type Ia classification and to measure the redshift. The whole process required coordinated use of multiple telescopes with rapid scheduling and was difficult enough that the technique was widely considered unreliable as recently as 1992. By 1996 and 1997, both teams had refined the technique to the point that they could deliver supernovae at redshifts around 0.5 with some regularity. The teams had developed the corrections needed to account for stretch and color and host galaxy effects. They had begun to publish preliminary results. The preliminary results were broadly consistent with the open universe interpretation, with omega m around 0.3 and no cosmological constant. They did not yet point to acceleration. They pointed, in early 1997, to a universe that was decelerating but more slowly than would be expected for a closed universe. The shift to detecting acceleration came in late 1997 and early 1998. As both teams pushed their measurements out to redshifts above 0.5 and began to combine their distant samples with the nearby supernova samples that had been collected over the previous decade, the combined fit in both teams started to favor a negative deceleration parameter. The supernovae at high redshift were dimmer than the open universe prediction. They were dimmer than the flat universe prediction. They were dimmer than the closed universe prediction. The only fit that worked was one with a cosmological constant providing about 70% of the energy density of the universe, with matter providing about 30% and with the geometry flat. Brian Schmidt, in interviews many years later, described the months of late 1997 and early 1998 as the most stressful of his career. The result was not the result anyone had been expecting. It contradicted decades of cosmological assumption. Both teams spent weeks and then months trying to find the error in their analysis. Was the stretch correction wrong? Was there an evolutionary effect in the type Ia supernovae at high redshift that made them intrinsically dimmer? Was there some kind of intervening dust that was reddening the distant supernovae? The teams checked each of these systematics separately and found nothing that could plausibly account for the result. The supernovae really were dimmer. The universe really was accelerating. There really was, by inference, a cosmological constant. The High Z team's discovery paper was led by Adam Rees then a postdoctoral researcher at the University of California, Berkeley, working with Schmidt's group. It was titled Observational Evidence from Supernovae for an Accelerating Universe and a Cosmological Constant. It was published in the Astronomical Journal, Volume 116, page 1009, in 1998. It used 16 Type Ia supernovae at redshifts between 0.16 and 0.62. The result, after the full analysis, was an omega lambda of about 0.7 with significant uncertainty, an omega m of about 0.3 and a deceleration parameter of negative 0.5 or so. The universe was, beyond reasonable doubt, within the sample's statistical reach, accelerating. The Supernova Cosmology Project's discovery paper was led by Saul Perlmutter and was titled Measurements of Omega and Lambda from 42 High Redshift Supernovae. It was submitted to the Astrophysical Journal in early 1999 and published in Volume 517, page 565, that same year. It used 42 Type Ia supernovae out to redshift 0.83. The result was nearly identical to the High Z team's result. Omega lambda around 0.7, omega m around 0.3. Acceleration confirmed. The fact that two independent teams, with different supernova samples, with different analysis methods, with different lead authors, and different institutional affiliations, had arrived at the same impossible result in the same year is what made the discovery stick. Either both teams had made the same fundamental mistake in the same way at the same time, or the universe was accelerating. The physics community, after the better part of a year of skeptical scrutiny, settled on the second option. The discovery was named the Breakthrough of the Year by the journal Science for 1998. The cosmological community spent the following decade refining the measurements. The supernova samples grew larger. The systematic corrections grew more sophisticated. The cosmic microwave background measurements from the Wilkinson Microwave Anisotropy Probe in 2003 and from Planck in 2013 confirmed the same dark energy density by an independent method using different physics. The baryon acoustic oscillation measurements from the Sloan Digital Sky Survey, beginning in 2005, confirmed it again. By 2010 or so, the existence of a non-zero cosmological constant dark energy of some kind, with a value somewhere near 68% of the critical density, was the most robust empirical result in cosmology after the Big Bang itself. The Nobel Prize in Physics for 2011 was awarded to Perlmutter, Schmidt and Riess for the discovery. The Nobel announcement, in the Royal Swedish Academy of Sciences press release, called the discovery one that would change our understanding of the universe. That was correct. It changed cosmology more fundamentally than any single result since Hubble's redshift distance relation in 1929. It introduced the cosmological constant as a real, measurable component of the universe. It established that the universe's energy budget was dominated by something nobody could explain, and it ended, for what looked at the time like permanently, the Big Crunch scenario as a serious candidate for the universe's future. The reason the Big Crunch died in 1998 was structural. The Friedmann equation, with a positive cosmological constant added, no longer permits recollapse in the conventional way. The cosmological constant, by definition, has a constant energy density. As the universe expands, the matter density dilutes. The cosmological constant does not. Over cosmic time, the cosmological constant's relative contribution to the energy budget grows, and the matter contribution shrinks. Eventually, the matter contribution becomes negligible. The expansion is then driven entirely by the cosmological constant, and the cosmological constant produces accelerating expansion. The universe enters an asymptotically exponential expansion phase, with the Hubble parameter approaching a constant value and the galaxy distribution diluting towards zero density. There is no recollapse. There cannot be with a constant lambda. The professional retirement of the Big Crunch was therefore not a matter of taste, it was a matter of math. Given the discovery of the cosmological constant in 1998, the recollapse case was logically excluded from the Standard Model. The only way to bring it back was to break one of the assumptions: either the cosmological constant was not actually constant, or there was some other component of the universe that physics had not yet detected, or the geometry was different from what was being measured. None of those options was, in 1998, taken seriously. The cosmological constant was constant. The geometry, measured by the cosmic microwave background, was flat to within fractions of a percent. There were no other detected components. The Big Crunch was, by the math, dead. What did not change in 1998 was the underlying mystery of why the cosmological constant has the value it has. The cosmological constant problem, as it became known, is the discrepancy between the value of lambda that quantum field theory predicts and the value that is actually measured. The theoretical prediction, computed from the zero-point energies of the various quantum fields populating the vacuum, is approximately 10 to the 120th times larger than the measured value. That is 120 orders of magnitude. It is the largest unexplained quantitative discrepancy in physics. It has been called the worst quantitative prediction in the history of science. It was a problem before 1998. The discovery of the cosmological constant turned it from a missing prediction problem into a wrong prediction problem. Physics now had a measurement of lambda, and the measurement disagreed with the theoretical calculation by 120 orders of magnitude. The cosmological constant problem has, in the years since, generated more theoretical work than any other unresolved problem in fundamental physics. None of the proposed solutions has been compelling. The problem sits, after 60 years of effort, essentially where it started. And if dark energy is not constant, the problem may need to be rethought entirely. A cosmological constant, whose value is not actually constant, is no longer a vacuum energy quantity in the standard sense. It is something more dynamic, a scalar field perhaps, or an evolving condensate, or an interacting component of the dark sector. None of those possibilities solves the problem. They change the structure of what physics is trying to explain. What the DESI data has done, in 2024 and 2025, is reopen exactly the assumption that was used to retire the Big Crunch. The cosmological constant might not be constant. If it is not, the math that retired the Big Crunch no longer fully applies. The Big Crunch is not, by the math, dead anymore. It is alive again. It has been alive for about 20 months. Part 8. The reopening what dark energy decay actually means. The class of scenarios that DESI's data has reopened, and that allow a Big Crunch to occur in a flat geometry universe with the matter density we actually measure, falls under the general heading of evolving dark energy. The simplest version of evolving dark energy is a single scalar field, often called quintessence, which provides a dark energy-like contribution to the Friedmann equation, but whose value changes over cosmic time. The scalar field rolls slowly down some potential. As it rolls, its effective equation of state changes. In the early universe, when the field is near the top of its potential, the field behaves nearly like a cosmological constant, with W close to -1. As the field rolls down the potential, W drifts upward, becoming less negative. If the field eventually settles at a minimum of the potential where the effective potential energy is zero, the dark energy contribution to the universe disappears entirely, and the universe is left with only matter and radiation to determine its dynamics. In such a scenario, the universe's future depends on what the matter density does in the limit where dark energy has fully decayed. If the matter density is still above some threshold, the the universe slows, stops, and recollapses. If the matter density has diluted enough, the universe simply coasts to an asymptotic state. The quintessence scenario is the simplest one. It does not, however, produce the phantom crossing feature that the DESI data prefers. The DESI fit has the equation of state going from below -1 in the past to above -1 today. A canonical quintessence field cannot do that. The proof, as mentioned earlier, is a theorem about the stability of scalar fields with canonical kinetic terms. The proof is not a loophole-free guarantee. It can be evaded by introducing non-canonical kinetic terms, by coupling the dark energy field to other fields, or by working in modified gravity frameworks, but it does mean that the DESI signal, if taken at face value, requires something more elaborate than the simplest quintessence model. The two-field models are the next step up in complexity. They involve two coupled scalar fields, one of which has a canonical kinetic term, and one of which has a non-canonical or k-essence-like kinetic term. The combined system can produce a phantom crossing without instability, because the two fields together carry stress-energy properties that the individual fields cannot. The cost is that the model has more parameters and is harder to motivate from a fundamental physics standpoint. The reward is that it fits the DESI data while preserving the underlying field-theoretic consistency. The interacting dark energy models go further. They posit that dark energy is exchanging energy with cold dark matter through some coupling that is not part of the standard model. The exchange modifies the dilution behavior of both components. Dark matter no longer scales purely as 1 over volume. Dark energy no longer has a fixed equation of state. The combined system can produce a wide variety of effective dark energy histories, including phantom crossings, depending on the form of the coupling. These models have the advantage that they can also address the Hubble tension by modifying the relative contributions of matter and dark energy in a way that affects the inferred Hubble constant from cosmic microwave background measurements. Then there is the family of models that produces the strongest recollapse predictions. These are the models in which the dark energy density itself eventually becomes negative. The simplest version is a slow decaying cosmological constant that decays past zero into a small negative effective value. The mechanism is some kind of vacuum energy bleed, in which the effective vacuum energy density slowly leaks out of the dark energy sector and into something else, leaving behind a residual negative contribution to the Friedmann equation. The detailed physics of how this works is model-dependent. The empirical consequence is straightforward. If the dark energy density is small and negative in the future, the universe stops expanding and begins to contract, with the contraction accelerating as the negative dark energy term grows in magnitude. Adil, Mukherjee, and Sen worked through this in detail in their April 2024 paper in ArXiv preprint 2404.10197. They fit a class of models in which the dark energy density was allowed to evolve from positive values today to negative values in the future, with a free parameter controlling the rate of decay. They found that the parameter space, consistent with the DR1 data, included scenarios in which the universe recollapsed on timescales of about 30 to 100 billion years. The wide range reflected the freedom in how aggressively they were willing to extrapolate the decay rate past the data window. The papers that followed, through the rest of 2024 and into 2025, refined these calculations using the DR2 data and various improvements in the parameterization. The general conclusion was the same. DESI-consistent scenarios with negative effective dark energy produce recollapse on timescales in the tens of billions of years. And the timescale is set primarily by how aggressively the dark energy evolution is allowed to continue. The crucial distinction between the modern Big Crunch scenarios and the textbook Big Crunch of the 1970s is the role of the geometry. The textbook Big Crunch required positive spatial curvature. The universe had to be closed. Planck 2018 has ruled this out. The spatial curvature is, to within 0.5%, 0. The universe is flat. The textbook Big Crunch is therefore dead by the geometry, exactly as it has been since 1998. The modern Big Crunch is not driven by the geometry. It is driven by the dark energy term. In a flat geometry universe with a small, negative, effective dark energy density, the universe still recollapses. The mechanism is not the gravitational pull of matter overcoming an expansion that is too slow to escape. The mechanism is the negative dark energy term acting as a decelerator that eventually overcomes the matter dilution. The timescale is set not by the matter density, but by the dark energy evolution rate. The closed universe textbook Big Crunch is a recollapse from above. The modern dark energy decay Big Crunch is a recollapse from below. The energy density of the universe falls through zero, and the universe contracts as a result. That is the scenario the DESI data has reopened. It is not the only scenario consistent with the data. The simpler quintessence models do not recollapse. The asymptotic coast scenarios do not recollapse. The textbook lambda cold dark matter scenario does not recollapse. The DESI data is consistent with all of these, but it is also consistent in the more aggressive extrapolations of the CPL parameterization with the negative dark energy recollapse. And the central values of the fit lie close enough to the edge of that scenario that the recollapse is no longer mathematically excluded. This is a fact that is worth sitting with for a moment. The Big Crunch, in its modern form, is not a closed universe scenario. It is a flat universe scenario with a particular kind of dark energy evolution. The flatness of the universe, which has been the central observational fact of post-inflation cosmology for the last 20 years, does not by itself rule out recollapse. The flatness rules out the closed universe Big Crunch. It does not rule out the flat universe dark energy decay Big Crunch. That distinction is, in 2026, the conceptual move that the field is having to internalize. For most of the field's working assumptions, dark energy is constant. The constant assumption is what made the post-1998 models so simple. With constant dark energy and a measured matter density, the universe's future is completely determined. There is no freedom left. The expansion continues forever, with the asymptotic behavior set by the constant lambda. Heat death is, in that model, inevitable. The moment dark energy stops being constant, that determinism breaks. The future is no longer a single trajectory. It becomes a family of trajectories, parameterized by the future evolution of the dark energy equation of state. Some trajectories lead to heat death, some lead to asymptotic coasting, some lead to soft recollapse on 100 billion year timescales, some lead to a hard Big Crunch ending in a singularity. The data does not yet pick out which trajectory the universe is on. The data only widens the parameter space of plausible trajectories. There is one more piece of context that matters here. The Hubble tension is, again, relevant. Models that have evolving dark energy with the right kind of decay structure to fit the DESI data also tend to reduce the Hubble tension. The two anomalies seem to live in the same family of model modifications. They are two different observations using two different techniques, and the fact that the same class of dark energy modifications addresses both is a kind of consilience that scientists pay attention to. Two anomalies pointing in the same direction is harder to dismiss than one anomaly on its own. The modifications that produce the DESI signal also produce, in some of their realizations, a recollapsing universe. That is the chain of reasoning that has put the Big Crunch back in the conversation. It is not, by itself, a prediction. It is a chain of reasoning that, given the data we have, is no longer ruled out. The textbook ending is not guaranteed. The recollapse ending is no longer impossible. The asymptotic coast ending is also alive. The next decade of cosmology will, slowly, narrow these alternatives. For now, the universe sits, somewhat unexpectedly, in a parameter space where more than one ending is allowed. The mathematics is clean, the physics is consistent. The reasoning is, given the data, not unreasonable. What remains is to ask what the recollapse would actually be like if it happens. What does the universe stopping look like from inside? What would the night sky do? What would the cosmic microwave background do? What would the cosmic event horizon do? Those are the questions the next part of this video is about. And the answers, like the data, are unexpectedly quiet. Part 9. What stopping looks like from inside. Imagine, for a moment, that you could sit at some location in the universe many tens of billions of years from now and watch the expansion stop. Not the end, just the moment of stopping. The moment the Hubble parameter passes through zero, the moment, in some technical sense, the universe ceases its outward motion and reverses direction. There would be nothing dramatic to see. There would be no boundary striking. There would be no force visibly arriving. The galaxy clusters around you, which had been receding for the last 80 billion years, would simply slow. Their redshifts would gradually decrease. The far galaxies, which had been receding fastest, would slow first. The nearer galaxies, which had been moving more slowly, would slow last. The redshifts on the most distant galaxies would, over a long span of time, approach unity. The redshift of unity is the value where the wavelengths arrive at exactly their emitted values. No stretching, no compression. It is the line where expansion and contraction are exactly balanced. The far galaxies would cross that line first. The nearer galaxies would cross it later. After the crossing, the redshifts would invert. The far galaxies would begin to blue shift. The light from them would arrive with wavelengths shorter than the wavelengths at which they were emitted. The blue shift would be small at first. It would grow over the next several billion years. The blue shift would deepen as the contraction accelerated. By the time the universe had been contracting for, say, 10 billion years, the blue shift on the most distant galaxies would be substantial. The light from those galaxies, which had been red in our era, would be shifted toward shorter wavelengths. The cosmic microwave background would do something similar. The CMB, currently at a temperature of about 2.725 Kelvin, has been redshifted by the expansion of the universe from its emission temperature of about 3000 Kelvin. The blue shift it would experience in a contracting universe would gradually undo that redshift. The CMB temperature would slowly rise. Over the course of, say, the first 20 billion years of contraction, it might rise from 2.7 Kelvin to 3 or 4 Kelvin, over the next 20 billion years to 10 or 15. The night sky, by this point, would be measurably warmer than it had ever been in cosmological history. This is the first thing to understand about a universe stopping and reversing. It would not be experienced as an event. It would be experienced as a long, slow change in the texture of the cosmos. The sky would brighten, the far galaxies would slowly approach, the CMB would warm. There would be no moment of decision. There would be no announcement. The universe would simply begin, gradually, to come back, continue the picture forward. The CMB warms past 10 Kelvin, then past 100. The night sky begins to glow visibly with thermal radiation. The far galaxies, which have been approaching for tens of billions of years, are now closer to us than they have been in cosmological time. Their light is blue shifted to wavelengths shorter than visible. The radio signals from distant galaxies, which propagated through 10 billion years of expansion to reach us, are now arriving compressed to higher frequencies, with energies several times their emitted values. By the time the CMB temperature has reached 3000 Kelvin, the universe has reached the temperature it had at the moment of recombination. At that temperature, hydrogen atoms are ionized again. The free electrons in the universe begin to scatter photons. The universe, which has been transparent since recombination 13.8 billion years ago, becomes opaque. The night sky, instead of showing distant galaxies and a faint thermal background, fills with a uniform, dense, hot plasma at the same temperature throughout. Stars, if any still exist, become invisible against the brightness of the sky. The Milky Way, by this point, has long since merged with Andromeda and the rest of the local group into a single elliptical galaxy. The merged galaxy continues to evolve, but its visible features are progressively hidden behind the hot CMB plasma. The contraction continues. The plasma heats. The CMB temperature rises past 10,000 Kelvin, past 100,000, past 1 million. The universe enters states of energy and density it has not been in since the first second after the Big Bang. The free electrons and ions become a fully relativistic plasma. The plasma reaches energies at which atomic nuclei begin to dissociate. The contraction is, by this point, exponentially fast, and the universe is racing toward Planck densities. This is what the recollapse looks like, in broad strokes, from inside. It is not, in any way, like a horror movie. It is not, in any way, sudden. It is the slow, quiet reversal of a process that has been running for 100 billion years. For a sleep-pacing pause, sit with that image. The universe is not ending. The universe is, slowly, coming back. The far galaxies are approaching. The CMB is warming. The night sky is brightening, degree by degree, over 1 billion years per degree. There is nothing to fear. There is nothing to do. The universe is simply, gently, reversing its long outward motion. What this reversal does not do is reverse time. The arrow of time, in the contracting universe, still points forward, entropy still increases, memory still works, causality still runs forward. The Penrose-Weyl curvature hypothesis, which we discussed in an earlier video, says exactly this. The initial state of the universe, at the Big Bang, was a low entropy state with vanishing Weyl curvature. The final state, at any recollapse singularity, would be a high entropy state with diverging Weyl curvature. The two states are not time reverses of each other. They are structurally different. The contraction is a continuation of the same arrow of time, not a reversal. This matters because it answers a common fringe interpretation of the Big Crunch, the idea that a contracting universe runs backwards in time, undoing events. It does not. The contraction is, from the perspective of any observer inside it, the same kind of forward-running cosmic process that the expansion was. Events happen. Time flows. The universe just happens to be getting smaller instead of larger. The cosmic event horizon does something interesting in this scenario as well. The cosmic event horizon, currently at about 16.6 billion light-years proper distance, is the boundary beyond which any signal we could send today would never reach. It is the boundary defined by the future evolution of the expansion rate. In an accelerating universe, the event horizon shrinks over time. In a universe that decelerates and then recollapses, the event horizon stops shrinking. It stabilizes. Then, as the contraction begins, it begins to grow. Galaxies that cross the event horizon outward, becoming unreachable, may, in a recollapsing universe, eventually come back into causal contact. This is one of the most striking structural features of a recollapsing universe. The event horizon is not a one-way street. In an asymptotically expanding universe, it is. Once a galaxy crosses outward through the event horizon, no message from us can ever reach it again. In a recollapsing universe, that exile is temporary. The galaxies that crossed outward through the cosmic event horizon during the expanding phase return eventually to causal contact during the contracting phase. The connections that the accelerating expansion severed are slowly, over tens of billions of years, restored. Consider what this means for the texture of the cosmos in the very late expanding phase versus the recollapsing phase. In the late expanding phase, the universe is increasingly fragmented. Galaxy clusters are isolated. The cosmic event horizon is shrinking. Each isolated cluster sees itself as the only structure left in a steadily emptying sky. By the time we are 80 or 90 billion years into the expansion, the extragalactic sky has gone effectively dark for most observers. A far future astronomer in our galaxy would see the merged Milky Way Andromeda as the only galaxy. There would be no evidence of cosmic structure beyond it. The universe would look, from inside, like a static island universe surrounded by an empty sky. In the recollapsing scenario, that emptying reverses. The cosmic event horizon stops shrinking, stabilizes, and begins to grow. The galaxies that had crossed outward come back into view. The sky, instead of darkening progressively, begins to brighten. The cosmic structure that had been fragmenting reassembles in a slow, stately, gravitationally driven approach. Galaxy clusters that had been receding past the horizon return to causal contact. The texture of the cosmos, instead of being one of isolation, becomes one of reunion. That is the central conceptual feature of the dark energy decay Big Crunch. It is not a contraction toward a final point. It is, for the first 100 billion years or so of the contracting phase, a slow reunion of the structures that the expansion had spread apart. The fragmentation reverses. The far galaxies, which had been one-way exiled, return. There is something almost gentle about this picture. The textbook image of a contracting universe is one of compression, of objects being pushed together by some external force, of the eventual mathematical collapse to a singularity. The actual picture, in the early phases of contraction, is the opposite. It is a picture of return. The universe gently, slowly, reels in the structures that have been receding for hundreds of billions of years. There is no force pushing them. There is no boundary striking. The expansion, having driven them apart, simply reverses, and they come back. The full implications of this reversal, for the texture of cosmological observation, take a long time to play out. The slow warming of the CMB occurs over billions of years. The slow brightening of the night sky occurs over similar timescales. The slow approach of the far galaxies occurs across tens of billions of years. From the perspective of any observer, at any single moment, very little changes. From the perspective of cosmological time, the universe gradually reassembles itself. That is what happens when it stops. Not a horror, not a sudden event. A slow, patient reunion of everything the expansion has been pulling apart. The far galaxies return. The CMB warms. The sky brightens. The cosmic event horizon, the one-way membrane that has been quietly closing for billions of years, opens back up. There is no force needed to make this happen. The geometry simply runs in reverse, and the listener, sitting somewhere inside this slow reunion, would not, at any single moment, notice anything dramatic. The universe stopping looks, from inside, like nothing at all happening until you compare the night sky now to the night sky a billion years ago, and notice that the far galaxies are no longer receding. They have begun, quietly, to come back. Part 10. The forces unwind. Push the contraction far enough forward, and the universe stops looking gentle. The reunion phase, which we have just spent some time inside, gives way to a phase in which the contraction is accelerating, the density is climbing, and the temperature is rising at a rate that, in retrospect, makes the gentleness of the early contraction phase seem like a long pause before the real event. This is the phase that the term Big Crunch usually evokes, the phase where the mathematics begins to break down and the universe approaches a singularity in finite proper time. It is worth being precise about what this phase looks like, because the description has a structure that mirrors, almost perfectly, the description of the very early universe in reverse. Cosmologists who have studied the recollapse scenario describe it as a time-symmetric counterpart to the Big Bang, not because the arrow of time runs backwards, as we have already established, but because the sequence of energy regimes that the universe passes through, as it contracts toward the singularity, is the same sequence it passed through, in reverse order, as it expanded from the Big Bang. The universe ends where it began. The end is the same energy ladder, climbed in the opposite direction. Start from the point where the CMB temperature has reached recombination about 3000 Kelvin. Continue the contraction. The plasma heats. The CMB rises past 10,000 Kelvin. The universe enters a fully ionized plasma state. Atoms are fully dissociated. Free electrons and ions move at energies high enough that no bound states can form. The contracting universe, in this phase, is the inverse of the recombination epoch. It is the moment when the universe stops being transparent and becomes, again, an opaque, hot plasma. Continue further. The plasma heats past 100,000 Kelvin, past 1 million, past 1 billion. At 1 billion Kelvin, the universe enters the regime where nuclei begin to dissociate. Helium nuclei break apart into protons and neutrons. The light elements that nucleosynthesis produced in the first 3 minutes of the Big Bang are, in the contraction phase, undone. The energy required to break a deuterium nucleus is about 2.2 million electron volts. The temperature at which deuterium nuclei thermally dissociate is around 10 to the 10th Kelvin. The contracting universe passes through that temperature, and the deuterium to proton-neutron conversion runs in reverse. Higher still. At 10 to the 12th Kelvin, the universe is hot enough that protons and neutrons no longer remain confined. The strong nuclear force loses its ability to bind quarks into hadrons. The universe enters a quark-gluon plasma state. This is the state that physicists have produced briefly in heavy ion collisions at facilities like the Large Hadron Collider's ALICE detector and the relativistic heavy ion collider at Brookhaven. The recollapse, by the time it reaches this regime, has the universe spending some finite time in the quark-gluon plasma state that the early universe occupied at about 1 microsecond after the Big Bang. The contraction continues. The temperature climbs. At 10 to the 15th Kelvin, the universe enters the regime where the electroweak unification is restored. The Higgs field's symmetry breaking, which gave the W and Z bosons their masses, undoes itself. The W and Z bosons become massless, like the photon. The electroweak force becomes a single unified force again, as it was in the first picosecond after the Big Bang. The Higgs field's vacuum expectation value, the number that determines the masses of fundamental particles, falls towards 0, higher still. At temperatures approaching the grand unification scale, around 10 to the 28th Kelvin, the strong force and the electroweak force may become unified into a single grand unified force. This is speculation at the level of fundamental physics. The Standard Model does not require a grand unified theory, and the experimental evidence for one is indirect at best. But the energy scales the universe would reach in the late contracting phase are high enough that, if grand unified theories are correct, they would become relevant. Higher still. At the Planck scale, around 10 to the 32nd Kelvin, the universe reaches energy densities at which gravity itself becomes a quantum mechanical force. The classical description of general relativity breaks down. The notion of space-time, as a smooth manifold, loses its meaning. The mathematics that has been used to describe everything up to this point, Einstein's field equations, the Friedmann cosmological solutions, the Standard Model of particle physics, all break down. What replaces them is, as of 2026, unknown. There is no agreed-upon theory of quantum gravity. There are candidates string theory, loop quantum gravity, asymptotic safety, causal dynamical triangulations, and others, but none has been confirmed experimentally, and the predictions of the different candidates for what happens at Planck densities differ significantly. What the mathematics of general relativity, by itself, predicts at the end of a recollapse is a singularity. The scale factor of the universe goes to zero in finite, proper time. The energy density diverges. The space-time curvature diverges. Every physical quantity that can be calculated diverges. The mathematics, in a literal sense, predicts the end of mathematics. The singularity is, in the language of general relativity, a place where the equations stop making sense. The Big Bang singularity, at the other end of cosmic time, has the same structure. The Big Bang, in pure general relativity, is also a singularity where the scale factor goes to zero and the curvature diverges. Every physical quantity is undefined. The mathematics breaks down. The Big Bang and the Big Crunch are, in the classical theory, time-symmetric singularities at the two ends of cosmic history. They are not events that physics can describe. They are limits of the equations that physics has. What this means, in practice, is that the question of what happens at the singularity is not a question that classical general relativity can answer. The question is a quantum gravity question. The quantum gravity question is, in 2026, unresolved. The different candidate theories make different predictions. Some predict that the singularity is real and that the universe ends there. Others predict that quantum gravity effects smooth out the singularity and the universe rebounds into a new expanding phase. Others predict that the universe undergoes some kind of phase transition that produces a qualitatively new state of cosmic geometry. We will come back to those possibilities in the next part. For now, the picture is this. If the universe recollapses, and if the recollapse continues all the way to Planck densities, then the universe enters a regime where the laws of physics as we know them break down. The mathematics predicts a singularity. Whether the singularity is real, or whether quantum gravity smooths it out, is a question physics cannot currently answer. The end of a Big Crunch, in the classical picture, is a mirror of the Big Bang, the same energy ladder, the same forces unifying, the same plasma states, the same approach to mathematical breakdown. The universe, in the contracting phase, climbs the same ladder it climbed in the expanding phase, but in the opposite direction. The ladder begins with neutral atoms and a transparent universe. It rises through the ionized plasma, through quark-gluon plasma, through electroweak unification, through grand unification, and into the regime where gravity becomes quantum mechanical. At the top of the ladder, the mathematics breaks down. There is a kind of structural symmetry to this picture that has fascinated theorists for decades. The universe begins with a singularity. The universe ends with a singularity. The two singularities are, in general relativity, formally identical. They differ only in the orientation of cosmic time. The beginning singularity sits in the past of all events. The ending singularity sits in the future. But the physics at each singularity is, in the classical theory, the same. This symmetry has driven a number of speculative cosmological proposals. Penrose's conformal cyclic cosmology, which we will discuss in the next part, proposes that the infinite far future of one aeon, a heat-death-style ending, not a recollapse, is conformally identified with the Big Bang of the next. Steinhardt and Turok's cyclic model proposes that the universe undergoes a sequence of expansions and contractions driven by the collision of two branes in a higher dimensional bulk. The loop quantum cosmology proposal of Ashtekar, Pawlowski, and Singh in their 2006 paper in Physical Review Letters, Volume 96, page 141301, proposes that quantum gravity effects produce a bounce at Planck densities and the universe rebounds into a new expanding phase. Each of these proposals is, in some sense, an attempt to fill in the gap that general relativity leaves at the singularity. Each of them says, in different language, that the singularity is not really the end. Each of them proposes a mechanism by which the universe continues past the moment when the mathematics breaks down. None of them is, in 2026, established. All of them are theoretical proposals that have not been observationally confirmed. What can be said with confidence is this: the classical recollapse, taken at face value, ends in a singularity. The singularity is where the math breaks down. What replaces the math is a question of quantum gravity, which is itself a question that physics has not yet answered. The recollapse takes the universe back through the same energy regimes it passed through in the expanding phase in reverse. The forces unify, the plasma heats. The mathematics, at the end, fails. There is one feature of this picture worth dwelling on for a moment. The recollapse, even in its dramatic final phases, is not a thing that any observer ever experiences as a single event. The final approach to the singularity is exponentially fast, but every step along the way is itself a continuous evolution of the universe's state. There is no moment when the universe suddenly transitions from existing to not existing. There is, instead, a continuous approach to a state in which the mathematics no longer describes anything. The universe, in the recollapse picture, does not end suddenly. It ends, mathematically, as a limit. It is a limit that no observer reaches, because there is no observer left at the limit. The observers have, by the time of Planck densities, long since been disassembled into the relativistic plasma. That is the end of the recollapse. In the classical picture, the universe climbs the energy ladder in reverse. The forces unify. The mathematics breaks down. The singularity is reached, formally, in finite proper time. What happens after, if the word after even applies, is the question the next part is about. Part 11. After the end, if there is an after. The question of what happens at the singularity is, in 2026, an open question. The classical mathematics of general relativity says that the universe ends in a point of infinite curvature and undefined physics. The various candidate theories of quantum gravity say different things. Some of them say the singularity is real and the universe ends. Some of them say quantum gravity smooths it out and the universe rebounds. Some of them say the singularity is replaced by a transition to a qualitatively different geometric phase. None of the candidate theories has been confirmed. The question is, at the level of fundamental physics, undecided. The most discussed proposal for what happens after a big crunch is the loop quantum cosmology bounce. In the loop quantum gravity framework, developed by Abhay Ashtekar and his collaborators over several decades, the geometry of spacetime is quantized at the Planck scale. The continuous classical manifold gives way to a discrete quantum structure. In their 2006 paper in Physical Review Letters, Volume 96, page 141301, Ashtekar, Pawlowski, and Singh showed that, in a simplified cosmological model, the discrete quantum geometry produces a repulsive force at Planck densities that prevents the singularity from forming. The contracting universe approaches a minimum scale factor of order the Planck length, then rebounds. The bounce replaces the singularity. The contracting branch of the universe smoothly transitions into a new expanding branch. The same physical laws apply on both sides. The universe, in this picture, is eternal, endlessly cycling through bounces, each bounce producing a new expanding phase that runs until the next contraction, and so on indefinitely. The textbook ending is not guaranteed. Neither is the recollapse. Neither is the bounce. Neither is anything the universe has agreed to. The Steinhardt-Turok cyclic model, set out in their 2001 paper in Physical Review D, Volume 64, page 123522, takes a different approach. In their framework, the universe is the four-dimensional brain embedded in a higher-dimensional bulk, and cosmic evolution is driven by the periodic collision of our brain with a second brain that lives elsewhere in the bulk. Each collision produces what looks, to observers on the brain, like a big bang. The universe then expands, dilutes, accelerates, and eventually approaches a near-empty state. Then the two brains approach each other again. Then they collide. Then a new expanding phase begins. The cycles run indefinitely. The cyclic model has the structural advantage that it does not require quantum gravity effects to produce the bounce. The bounce is produced by ordinary brain physics in a higher dimensional theory. The model does require, however, the existence of higher dimensions and the existence of the second brain, neither of which has any direct observational support. The model is theoretically self-consistent. It is also, observationally, indistinguishable from a standard cosmology over the past 13 billion years, which makes it neither confirmed nor refuted by current data. The Penrose conformal cyclic cosmology, set out in his 2010 book Cycles of Time, takes yet another approach. In Penrose's framework, each aeon of the universe ends not in a recollapse, but in heat death, the asymptotically expanding scenario, with dark energy keeping the universe in an exponential expansion forever. As the universe enters the deep heat death state, all massive particles eventually decay, and the universe is left with only massless particles, photons, and gravitons. A universe with only massless particles has, in a precise mathematical sense, no scale. The geometry of such a universe is conformally invariant, meaning all distances and times are arbitrary. Penrose proposes that this scale-free heat-death state is conformally identified with the scale-free Big Bang of the next aeon. The infinite far future of one universe becomes the infinitesimal Big Bang of the next. Penrose's model does not require a recollapse. It is, in fact, a cyclic cosmology of the heat-death-ending variety. It is included here because it is one of the live cyclic cosmology proposals, and because, if the DESI evolving W preference holds up but does not produce a recollapse, the universe could still end up cycling through Penrose's conformal handoff mechanism. None of these three cyclic models is currently established. None has direct observational support. The arguments for each are theoretical, structural, or aesthetic. The arguments against each are primarily that no current observation requires them. What can be said is that if the universe recollapses, the question of what happens at the singularity has at least three serious candidate answers. The singularity might be real, and the universe might simply end. Quantum gravity might smooth it out and produce a bounce. Brain physics, or conformal handoff, might connect the end of one universe to the beginning of another. Which of these is correct, if any, is a question the data has not yet been able to address. The textbook ending is not guaranteed. The recollapse is not guaranteed. The bounce is not guaranteed. None of the cyclic models is guaranteed. The universe sits, in 2026, in a parameter space where multiple endings are allowed and multiple after-endings are allowed. The next decades of cosmological observation will narrow some of these alternatives. Most of them will not be narrowed by the data we currently have. Some of them may never be narrowed at all if they make predictions that lie beyond what observational cosmology can reach. This is, perhaps, the most honest statement of where physics is on the question. The universe might expand forever. It might recollapse. It might bounce. It might cycle. The data does not yet say which. Part 12. The decimal that decides everything. Sit with where this leaves us. The universe might expand forever. It might slow and coast. It might stop, somewhere between 30 and 100 billion years from now, and gradually contract back through everything it has been. It might bounce. It might cycle. It might do something that no current candidate theory predicts at all. The fate of the universe sits, in 2026, in the third decimal place of a number that nobody alive understands the value of. The number is W, the equation of state of dark energy. The value of W determines, in concert with the matter density and the geometry, whether the cosmological constant wins forever or whether matter is allowed to win again at the end. If W stays at exactly -1, dark energy is constant and the cosmological constant wins. If W drifts towards 0, the cosmological constant decays and the universe could either coast or recollapse, depending on how the decay proceeds. If W crosses 0 into positive values, the dark energy term becomes a decelerator and the universe stops. The DESI data has, in 2024 and 2025, given the value of W today as approximately -0.8, with 1 sigma uncertainty of about 0.06. The data has given WA as approximately -0.75, with 1 sigma uncertainty of about 0.25. The two numbers, taken together, describe a dark energy history that is evolving. Whether the evolution is real, or whether it is an artifact of the supernova sample dependence or the parameterization choice, will be decided by the next decade of cosmological observation. What this video has been about is the structural fact that the question of the universe's ending has, after 27 years of professional retirement, been put back in front of the field by a single instrument doing patient work in the Arizona desert. The 5,000 fiber positioners on the Mail telescope are not, by themselves, going to settle the question. They are going to provide one input. Other inputs will come from Euclid, from the Vera Rubin Observatory, from the Roman Space Telescope, from the next generation of cosmic microwave background experiments. The field will, slowly, narrow the parameter space. The 5 sigma threshold for discovery will, in time, either be crossed or not. But the framing of the question has already changed. The textbook ending is not guaranteed. It has not been ruled out. Neither has the recollapse. Neither has the bounce. Neither has the cyclic. The universe sits in a parameter space wider than the one cosmology has been working in since 1998. Whether the parameter space narrows back to the textbook ending or whether it consolidates around a different ending is the work of the next 10 or 20 years. What happens when it stops? This was the question we opened with. The honest answer, 12 parts in, is that we do not yet know if it will. The data has not made the recollapse likely. It has only made it possible. It has only refused, for the first time in a generation, to rule it out. If it does stop, if dark energy decays through 0, if the negative dark energy scenarios consistent with DESI turn out to describe the real universe, then the stopping will not be experienced as an event. It will be experienced by any observer present at the time as a long, quiet reunion. The cosmic event horizon, which has been shrinking for billions of years, would stop and begin to grow. The far galaxies, which have been receding for tens of billions of years, would slow and turn around and approach. The night sky, which has been emptying, would brighten. The cosmic microwave background, which has been cooling for 13.8 billion years, would begin to warm. None of this would feel like ending. All of it would feel, on any timescale, shorter than 1 billion years, like nothing at all. The universe stopping would not, in any way, undo the events that had happened during the expansion. The arrow of time would still point forward. Memory would still work. Causality would still run forward. Everything that has ever happened would still have happened. The contraction would not, in any sense, run history backwards. It would just be the universe continuing forward through a phase of geometric reunion that gradually escalated over many tens of billions of years into the final approach to the singularity. There is something that might be called peace in this picture. The textbook ending, the eternal, accelerating expansion ending in heat death, is, structurally, an ending in isolation. Each gravitationally bound system becomes its own island universe, alone in an emptying cosmos, watching the rest of cosmic structure recede past the event horizon. The recollapsing ending is, by contrast, an ending in reunion. The structures that the expansion has been pulling apart return. The cosmic event horizon opens back up. The fragmentation reverses. The universe, on this picture, ends not by dispersing, but by gathering itself back together. Whether the universe is going to do this is, again, not something the data has yet decided. The DESI evolving W preference is below the discovery threshold. The result is sample dependent. The CPL extrapolation is a model assumption. The negative dark energy scenarios are one option among several. The recollapse is allowed by the data. It is not required. It is not even, on the central values of the DR2 fit, the most likely outcome. It is just no longer impossible. That is enough, for the purposes of this video, to make the question worth asking. The textbook ending is one ending among several. The big crunch is back in the conversation. The data, slowly and against its own framer's inclinations, has reopened a door that 1998 had professionally closed. What happens when it stops? The question is not yet a measurement. It is, for the first time in 27 years, a question the data has refused to settle. The third decimal place of a number nobody understands the value of will decide. The instrument that is going to decide it is, tonight, taking spectra. The fiber positioners on the 4-meter telescope at Kitt Peak are reseating themselves between observations, drinking in the light from galaxies that have been receding for billions of years, recording the redshifts, building the largest three-dimensional map of the universe ever made. The data is being collected. The question is being asked. Somewhere in the slow accumulation of those redshifts, the universe is telling us whether it intends to expand forever or whether it intends, at some quiet moment, many tens of billions of years from now, to stop. Sleep well. The universe will let us know.